Hi class. Well, it's the last chapter. Are you excited? Chapter 16 is going to focus on proteins. I've broken it up into two different lectures. So part one is going to focus on amino acids and polypeptides. So amino acids are the building blocks. They're the molecule that makes up polypeptides and proteins. So proteins are important in our body. There is nothing on this slide that I'm going to test you on. It has a lot of information, but I do want to spend just a little bit of time on it so you can get a feel for how important proteins are in our body. Proteins, they're structural proteins. For example, keratin, which is in our hair and skin and nails. Contractile proteins, which play a role in muscle movement. Transport proteins, which carry substances throughout our body, storage proteins to store nutrients, hormones, enzymes that catalyze reactions. Proteins also play a role in our immune system. So amino acids, as I said before, they're the building blocks of proteins. They're the molecules that we make proteins out of. They contain a carboxylic acid group and an amino group on an alpha carbon. So let me just refresh here for you real quick. So remember that carboxylic acids have that carbonyl group bonded to a hydroxyl group. So let me put my R on there. So this is a carboxylic acid. And remember, it can also be written abbreviated with the two O's in a row. So sometimes we will abbreviate a carboxylic acid like this. And then our amine groups, on your information sheet, it has the alkyl group to a nitrogen, and then it has these two lines. Because in organic chemistry, we learned that this nitrogen can be bonded to 3 carbons, or these could be to some hydrogens. In amino acids, we're always going to see it with the 2 hydrogens. So it's going to be kind of abbreviated like this. So amino acids have this amino group. If you take apart the word here, the amino part comes from the amine group, and then the acid comes from the fact it has a carboxylic acid side chain. The alpha carbon is the carbon here in the center that is bonded to the carboxylic acid group and the amine group. Amino acids can be ionized when you put them in solution. So over here on the left, I have it non-ionized. Notice there's no charge on this amino acid. But when you put them in solution, they end up becoming ionized, meaning they get these charges. So what happens is the hydrogen from the carboxylic acid group, because if you remember, that's one of our definitions of an acid, is when you put them in water, they donate the hydrogen ion. So this carboxylic acid in solution will donate this hydrogen ion, and the amines, which are bases, will accept the hydrogen ion. So that's why here we only have 2 H's, but over here we have 3 H's. So this third H comes from what used to be over here on the carboxylic acid side. Amino acids contain different R groups. So this R group up here, which is also called the side chain, and you'll hear me interchange those 2 words, so make sure you have that memorized. Amino acids have a side chain, which make it unique. This part down here of the amino acid is on every amino acid. So every amino acid is going to have an alpha carbon bonded to an amine group, to a carboxylic acid group, and to a hydrogen. Okay? It is this R group or side chain that makes the amino acid what amino acid it is. So for example, glycine, which is the most simple amino acid, its R group is just a hydrogen. When we look at alanine, the R group here is a methyl group. So once again, if you look at the rest of the amino acid, that is going to be the same in every amino acid. Okay, so it is just the R group that you want to be able to see. So where is the alpha carbon in alanine? I hope you come in here and you just pick this center carbon. That would be the alpha carbon. Okay, some of our amino acids are called essential amino acids. These are 10 amino acids that you can only get from your body, from your diet, because they are not synthesized in the body. Some of the other amino acids, it's not a big deal if you get them from your diet because our body can make them, but not these 10 essential amino acids. They are prevalent in meats and dairy products. If you are, however, like a vegetarian or a vegan, it is possible to still get these amino acids from some of your grains, but you have to definitely be intentional about what grains you're choosing to eat and things like that, so you can make sure you're getting these 10 essential amino acids. Amino acids are broken into 3 different categories. So the first group is called the nonpolar amino acids. These are hydrophobic, so remember, if they're nonpolar, they don't want to be around water, so we call that hydrophobic. And they have hydrocarbon side chains. The other category is polar, which are hydrophilic. You're going to know those because they have polar or ionic side chains. Your acidic amino acids, which are also hydrophilic, will have an acidic side chain, and your basic amino acids, which are also hydrophilic, will have the amine side chain. So let's look at those real quick. Here's an example of a nonpolar amino acid because the R group is just a hydrocarbon. So that's kind of tricky because when you look at this amino acid, your brain should be saying, well, that looks kind of polar to me. I'm seeing this positive charge here and this negative charge here, and technically it is a polar molecule. But when we classify it as being either a polar or a nonpolar amino acid, we just deal with the side chain. Okay, so this is a nonpolar amino acid because of that methyl group there. Here's an example of a polar amino acid, and that's because, remember, OH bonds are very polar. They can hydrogen bond. Here's an acidic amino acid because here's our carboxyl group. Some books actually put the hydrogen on here, so it's a little more obvious that this is our carboxylic acid with the carbonyl group to the hydroxyl group. But your book is leaving that hydrogen off, and they're having it as the ionized form. So these would be your acidic amino acids because the R group has a carboxyl group, and your basic ones, your R group has that amine group. So once again, your book here is showing it protonated where it has that hydrogen on it, the hydrogen ion. So be able to identify whether an amino acid is nonpolar, polar, basic, or acidic. So focusing on each one of those groups. The nonpolar amino acids you're going to be able to recognize because they have, the R group is either going to be it's either going to be the hydrogen, or the R group will be an alkyl group like a methane or an ethane, so a grouping that is just made of carbon and hydrogens, or it's going to have an aromatic side chain, which would be your benzene rings. So that's how you're going to identify your nonpolar groups. Your polar groups are either going to have an alkyl R group, a thiol, or an amide. So remember, you're going to identify your alcohols because they're going to have this OH group. The thiol is going to have an SH group, and your amides, if you remember, they have the nitrogen that is bonded to a carbonyl group. So if it has an amide, a thiol, or an alcohol, you're going to identify it as a polar amino acid. Your acidic amino acids, there's two of them, and here you're going to recognize them because it's going to have that carbonyl group, and then your book is having it here with the O minus. So be able to identify that as your acidic groups. Your basic groups are going to have an amine group, and you're always going to see it with the NH3 with the positive, or here's an NH with a positive. So if you have nitrogen with 4 bonds going to it, then that's going to be your basic amino acids. Okay, so here's a learning check. Identify these 2 amino acids as either being polar or nonpolar. Now, there's a lot of different ways of writing amino acids, so you need to be careful. So the first thing you want to do is you want to identify that alpha carbon. So right here, the alpha carbon is the carbon in the center that's bonded to a nitrogen on one side, and it's got the carboxylic acid group on the other. So what I recommend doing is when you see it written like this, where the H's are put next to the alpha carbon, is take the hydrogens and write them out. So take them out of that parent chain in one line. So this guy right here, the R group is a hydrogen ion. So you should say that this first one, glycine, is nonpolar. When I get to this one, I'm going to rewrite this H coming down here. Okay, so here's my amino group, the hydrogen, and the carboxylic acid group that is on every amino acid. What makes this amino acid threonine is this R group right here, this side chain. And if you look at it, you can see that it has a hydroxyl group, which means this one's going to be a polar amino acid. So amino acids are all chiral except glycine. So if you remember glycine, it had the hydrogen R group. So that was a non-chiral, an achiral molecule. But other than glycine, all of the other ones are chiral. They're going to be bonded to 4 different groups. In which case, since they're chiral, if you remember, then their mirror images are going to be stereoisomers of each other. So here is the L-alanine, and if we have a mirror here, the D-alanine is the mirror image. And it's chiral because this alpha carbon here in the center is bonded to 3 different groups. So it's a chiral molecule. The Fischer projections have stereoisomers, like I said. It is the L form of the amino acids that our bodies use in making proteins. So our bodies don't use the D stereoisomer. Zwitter ions are charged. They have the charged amino group and the carboxylic acid group. So they form from both the amino group and the carboxylic acid group when the amino acid is ionized in water. The Zwitter ion, when it has an equal positive and negative charge, we call that at the pi point, the isoelectric point. So I wish I kind of had this bolded and underlined for you, because I do want you to know the definition of the isoelectric point. So the definition is when it has equal amount of positive and negative charges. I also want you to notice the symbol we give for the pi, the isoelectric point. Okay, it's a lowercase p and a capital I. So here's an example. This is glycine when it's not ionized. So this one here on the left is not a Zwitter ion. But if we take this H off of the carboxylic acid and we put it over here on the amino group, and we leave a negative sign by where the H used to be and this positive sign over here, this is the Zwitter ion. Okay. The pi values for each of the amino acids are listed on their structure on the previous page. So when I first put on all the amino acids, underneath it has the pi. You're going to need to know that for your homework, because when you're doing the homework, you need to go to your textbook and look underneath the structures of the amino acids to get what their isoelectric point is. So in solutions that are more basic than the isoelectric point, so let me refresh your memory real quick on our base scale, our pH scale. pH ranges from 0 to 14. Now, when we were going through the acid-base chapter, I told you that 7 was neutral, right? And anything above 7 was basic, and anything less than 7 was acidic. So that's a true statement, but when we're thinking about amino acids, we want to forget about this 7 being neutral. We want to think about neutral to the amino acid being its isoelectric point, okay? So every amino acid has a different isoelectric point, but when the pH is equal to the pi, the isoelectric point, then that is when the amino acid is neutral. Okay, it's the same amount of positive charge as negative charge. So kind of forget about that 7 value being the neutral value when we're talking about amino acids. But I do still want you to remember that as the numbers get larger, you're getting more basic, and when the numbers get smaller, you're getting more acidic. Okay, that concept is still important. So in solutions that are more basic than the isoelectric point, the NH3, which is positive, in the amino acid is going to donate its proton. So if it's more basic, then this group is going to give up an NH+. So here's an example. Remember, our symbol for adding a base is this hydroxide ion. Okay? So if you are putting a base into the solution, your Zwitter ion, which part of this is going to react with the base? It is the NH3 positive group. And remember, it's going to lose an H+ to the base. So recall that amines are bases, so we learned that back in organic chemistry. So they're conjugate acids, and that is, you write the amine with an H+ on it. The conjugate acids are going to be acids which donate their H+. So what we're saying here is that this guy right here, when he's positive, he is an acid. And remember that acids neutralize bases. So if you have a high pH compared to the isoelectric point, then your NH3 positive group is going to donate a hydrogen ion to that base. In solutions more acidic than the pi, the carboxylic acid group in the Zwitter ion, so it will have already lost its hydrogen ion. This group, the COO- in the amino acid, is going to accept a proton. And remember that the word proton is used to symbolize our hydrogen ion. So a hydrogen ion from the acid is going to react with the COO- group on your Zwitter ion. So here is my symbolism for I'm adding an acid. Which part of my Zwitter ion is going to bond to this H+, and that is going to be this group. Okay, so this conjugate base of the carboxylic acid is going to accept the hydrogen ion from the acid. And I should have gone over this part here. So let me go back to the previous slide because I failed to mention this. When you have the Zwitterion, I'm focusing right here. When you are at a pH, so when the pH is equal to the pi, at the isoelectric point, the charge is going to be 0 because you have a +1 and you have a -1. So a +1 plus a -1 is going to sum up to be 0. When the pH is greater than the pi, your net charge is going to end up being this -1. Because remember, when you put your Zwitterion in a basic solution, it loses the H+. So, and that brings us down to just NH2 without that positive sign. So the net charge is going to be -1 because of this negative sign. That's not offset anymore by the positive. If we look at this slide here, if the pH is less than the pi, then the net charge on the amino acid is going to be a +1. And let's go back over that. The reason why is if you're in acidic solution where the pH is low, the COO- is going to accept that H+, and then it's no longer going to have a charge. So the only charge you have left is this +1 charge. Okay, so you need to be able to do that. I'm going to give you an amino acid. I'm going to tell you its pi, and then I'm going to tell you what pH that amino acid's in, and I expect you to be able to either draw it or tell me whether it is a net +1 or a net -1 charge. So here's kind of a summary of what I said. Here is my Zwitterion. Okay, and this is the form of the Zwitterion when the pH is equal to the pi. This is how you'll find the amino acid. If I put it in an acidic solution, so I'm lowering the pH, then my NH3 positive group, oh sorry, I said that wrong, the COO- group is going to bond to the H+ and become our carboxylic acid and leave us with a net +1 charge. So at a low pH you have a positive charge. And then the opposite here, if you've got a base, then that's going to react with the NH3+. The way I visualize it, I don't know if this is going to help you, but I like to think about it as I've got a beaker. And I think we're kind of, I hope anyway, you're familiar with the fact that if I put a lot of H+ in here, that this would be an acidic solution because acids donate their H+. And when I'm thinking about a basic solution, I visualize a beaker that has a solution with a whole lot of hydroxides because bases have a high pH. Okay, so I say to myself, when I put this Zwitterion into my acidic solution, do I think the H+ is going to react with my NH3+? And I hope you say no, because like charges are going to repel each other. My hydrogen ion wants nothing to do with this NH3+ side of my amino acid. But would it be attracted to the COO- charge? And I hope you, or side, and I hope you say yes, because opposites attract. So this negatively charged oxygen here is going to be attracted to this hydrogen ion. And so that's what's going to happen in a low pH, is the hydrogen ion is going to hop on that negative oxygen. When I think about putting this Zwitterion in a basic solution, I think of a whole bunch of hydroxides floating around, and they're going to be attracted to the positive side of my amino acid. And so they're actually going to steal then an H+ from this NH3, because the H+ plus the hydroxide then is going to balance and make water. So I don't know if that helps you, but that's kind of the visual I'm thinking of in my head when I'm trying to decide whether it's a net 1 positive charge or a -1. So here's a learning check. What is the predominant form of serine at a pH of 12? And I have to tell you the PI. I don't expect you to memorize any of the PIs. So I'm telling you that serine's PI is 6. And I want you to draw out the structure of serine when I put this Zwitterion in a solution that has a pH of 12. Okay, so the first thing I want you to brain to say is pH of 12 is higher than 6. Okay, so we are talking about putting him into a basic solution. So what I like to do is I like to think about dropping this amino acid into a solution that has a whole bunch of hydroxide ions because I'm at a high pH. So which side of my Zwitterion do you think is going to be attracted to these OH minuses? Do you think this side over here, the right side with its minus charge? And I hope you say no, because the two negatives are going to repel each other. So it's going to be this side right here that's going to be attracted to my hydroxides. And what do you think is going to happen? It's going to give up one of its H pluses to the hydroxides to make water. So I just have to rewrite this amino acid with one less hydrogen ion. So instead of having 3 H's, it's only going to have 2 H's, and it loses that positive sign. And then I just kind of keep working from left to right and recopy the rest of my amino acid. And I keep that negative. So remember here my pH is greater than my PI, and notice the net charge of the amino acid I drew is a -1 charge. So I want you to be able to do that. Okay, so that was amino acids. And remember, amino acids are the building blocks of proteins. They're also the building blocks of polypeptide chains, which I'm going to talk about here for a sec. So what happens when you put amino acids together is, on my pad. So we've got 2 amino acids. When you bond them together, we get what we call a peptide bond. So the peptide bond is holding your amino acids together. In this particular case, we call this a dipeptide. Di is the prefix for 2. So in a dipeptide, you have 2 amino acids. And you can do this reaction backwards. When you go this direction, it's called hydrolysis because you're going to break this apart with water. When you form the peptide bond, water is produced. So here's a kind of cute question. So how many peptide bonds are in a dipeptide? And it's kind of tricky because a lot of students want to say, oh, there's 2 dipeptide bonds. But remember, the peptide bond is the bond holding 2 amino acids together. So the answer to this question is going to be 1. There is 1 peptide bond in a dipeptide. So don't fall for that trick. Here's just a visual of what I just got done telling you. So the way you make a peptide bond is you take 1 amino acid and you take off the OH group from it. And then you're going to take a nitrogen from the amino group on the neighboring amino acid. So basically you're going to rope out water. So when you put amino acids together, water is one of your products. And then when I took off this OH group, this carbon here is now looking to make a new bond, and the nitrogen wants to make a new bond. So the carbon and the nitrogen will bond together, and that'll be our peptide bond. This is the same bond in organic chemistry that we call an amide bond. So an amide bond is the same as a peptide bond in biology. So, peptide formation. I just got done telling you it's an amide bond. It forms between the carboxylic acid group of one amino acid and the amino group of the next amino acid. So here is the amino acid part of one amino acid, and it is going to react with the amino group on another amino acid. And remember, you're taking out water. So you're going to take off this oxygen, and then how many hydrogens do you need to steal from this one? Hopefully you say 2, because we need to get water. So actually water should be one of the products here. So when you take 2 hydrogens off of this amino group, you're left with just a nitrogen to 1 hydrogen. So that's what they're showing here. Here's the 1 hydrogen that I left on there. And you make a new bond then between this carbon and the nitrogen. So I'm going to expect you to be able to do this amide formation for our peptides. Here's showing you the exact same thing using a ball and stick figure. So here's my carboxylic acid group. You're going to take off the oxygen and 2 hydrogens to make water. And then this nitrogen then is going to bond to this carbon to make our peptide bond. Here is a learning check. Actually, this is an example because I've got the answer for you here on the next slide. So write the dipeptide of serine to threonine. So what they do with polypeptides and proteins is they have these 3-letter symbols that they use to abbreviate the full name of the amino acid. But the order they put them in is very important. Okay, you're going to learn that when we get to the primary structure of proteins. But the order that the amino acids bond in play a big role in how the protein is going to fold. So here is an example where we're putting serine with threonine. And if I was going to write the products, I'm going to take off this oxygen and I'm going to take off 2 of these hydrogens, which is just going to leave us 1 hydrogen on the nitrogen. Okay? And so my answer is going to be this carbon bonded to this nitrogen, and then I'm going to have water as one of my products. So I have that for you here on this slide. Okay, so here is my peptide bond right there. So here, this was serine bonded to threonine. Now I would like you to write threonine bonded to serine. So basically you're going to look back the previous slide and put those two amino acids down in a different order. So I know you don't have this on your slide, but I went and cut and pasted these from the previous slide and rearranged them. So I have the threonine on the left and the serine on the right. I'm going to take the oxygen this time off the threonine, and I am going to take 2 of the hydrogens. I'm going to put this third hydrogen up here. I'm going to take these 2 hydrogens to make water. So I am going to start writing this thing from left to right. So I'm going to start here with my H3 and with its positive sign, going to a CH, and then up above I have I'm just going to put the H on the right side because I like that better. CH3. And then I'm keep going along. Then I have this carbon which has the double bond oxygen. Now here's where I have to change because I've taken off this oxygen. So what's going to bond to this carbon is the nitrogen on the neighboring amino acid. And I can write its one hydrogen either up or down, it doesn't matter. And then I'm just going to continue from here now. So I've got my nitrogen with its hydrogen going to the alpha carbon there, up to CH2OH, and then I have my carboxyl group. Okay, so here is a dipeptide with its one peptide bond. Make sure you can locate the peptide bond. So polypeptides, if you have 3 amino acids put together, we already said 2 was going to be a dipeptide, 3 amino acids is going to be tripeptide. So when you bond 3 amino acids, you get 1 tripeptide, and you're going to end up getting 2 water molecules. Many amino acids are called polypeptides because poly means many. When you get to the point where you have put approximately 50 amino acids together, that's when we start calling it a protein. Okay, proteins are long. So here is a question. How many peptide bonds are in a tripeptide? And I hope you said 2. Because in a tripeptide, we have 1 amino acid bonded to another amino acid bonded to a third amino acid. So you have 2 peptide bonds in a tripeptide.